Hello everyone. Today we are going to discuss together some problems. Okay, mainly I will focus on two problems. So it's more or less like the problem that will come in the midterm exam, just to train you how to solve the power problems and the three-phase problems. So for instance here, this example, we have two loads. Okay, let me open. Then from here. Okay, so as you can see here, guys, we have two different loads. This is load, assume this is load number one, and this is load number two. And now we need to make some analysis in this circuit. So firstly, we need to get the supply voltage. So we don't know the current here in this branch, which is the transmission line. And we need to get this supply volt. We solved in our class some problems like that before. So this is just a training how to do the same here in this problem. So for the first load, we have 50 kVA. So 50 kVA here, guys, this is considered as the apparent power. So this is S1, and the power factor is 0.95 leading. And here for load number two, we have 50 kilowatts. So this is active power. So this is P2, and the power factor is given 0.82 lagging. And then the transmission line, so this is Z transmission line equals real part 0.2 plus J 0.4. So this is the impedance, and here this is the supply of our circuit. Now, we need firstly to get the supply volt. In order to get the volt here, if you make Kirchhoff voltage loop here, so you need this current, okay, and the volt here. Actually, we know the volt here, so we know the volt at this part, which is nothing but the 480 volt, and the angle is 0, so this is a reference. And we need the current here in order to say Vs equals 480 plus the voltage drop across this transmission line. So the best way is to get the first current, I load 1, then get I load 2, and add them together in order to get I total. So this is a solution of this problem. So let's follow up step by step here. So here is my solution, guys. So firstly, I said here I1 of load 1 equals S divided V. You know the relation S equals V times I conjugate. So we can say S absolute value equals V absolute value times I absolute value. And the angle of current can be obtained from the power factor here, since the voltage angle is 0. So we can say the angle of power factor is cosine inverse the power factor, and if it is lagging, the angle will be negative. If it is leading, the angle will be positive. So why negative? Negative because the reference is 0. Okay. Why positive? In case of leading, it will be positive because the voltage is 0. So for the first load, it's leading power factor. So we can say now I1 equals S1 divided V, and the angle is cosine inverse power factor, and here it's a plus sign because this is leading power factor. So this is amount of S, so this is S of load 1, 50 kilovolt ampere, and this is a volt here, and cosine inverse our first power factor. And you will get this value of current. So this is the absolute value of current, and this is the angle. And again, as you can see, the angle is 18.19, and the volt is at angle 0. So if we draw the phasor diagram, this is V at angle 0, and I is leading V by 18 degrees. So this is I. So this making sense for us. This is leading. By the same way, we can get the current of the second load. So we can say now I2 equals, you know, the relation of power, active power equals V times I times power factor. So we can say I equals active power divide V power factor. and the angle is gonna be cosine inverse power factor, but here it's minus sign because he mentioned here for load number 2, the power factor is lagging. So the value of power is 50 kilowatts, the same volt for 80, and the power factor is 0.82, and the angle is negative as we mentioned, cosine inverse 0.82. So this is the value of the second current. Now guys, from the circuit we can say I total equals I1 plus I2. So we can say the overall current I total equals summation of the two currents, and you will get this value here, 207 at angle minus 11.19 ampere. So this means, guys, since the current angle is negative and we don't know the voltage here, so we cannot recognize the power factor. So this is the supply current, guys. So the supply current here is at angle minus 11 degrees. We cannot say the power factor is lagging or leading before of knowing firstly what the angle of Vs, the supply volt. So let's now solve the first part, which is the supply volt we needed. So we can say now Vs equals V load plus Z transmission line times I total. So V load equals 480 angle 0. This is the impedance of our transmission line times our current that we have calculated here. So you will get the voltage 541 at angle 7 degrees. So now guys, if we compare this angle, so if this is 0, this is V load. Now the supply volt Vs is 500 something. The first one, this one was 480, so 500 more than in length, and the angle is in positive sign. So we can say this is, for instance, the supply, and this is our angle, which is 7.77 degrees. So we can say this is Vs. And where is current? The total current is at angle minus 11.19. So the current here is at angle minus 11. So this is minus 11.19 degrees. And this is I total. So we can say, guys, I total is lagging Vs. So I total is lagging Vs. Let me write that. I total is lagging Vs, which means the supply power factor is going to be lagged in this case. So this was the first part, guys. We need to calculate the supply volt. The second part of the problem, part 2, we need to get the supply active power. You know that we mentioned before the relation of active power, you know, P active equals V times I times cosine theta V minus theta I. This is a general form of power. If you need the power from the supply here, so this means V supply times I total cosine theta V supply minus theta I total. Actually, we have V supply and we have I total now, so we can easily substitute now in this relation. So we can say here V supply times I total cosine theta V supply minus theta I total. So the V supply magnitude is 541. This is what we have calculated here. And the current is 206 to 207. This is the current magnitude, the total current. And cosine theta Vs, so this is theta Vs and this is theta I total. So 7.77, the voltage angle, minus 34.92. Okay. So it seems I made a mistake here. This should be the total current, which is minus 11 0.19, not the minus 30 something, okay? And now we can calculate this value again. And here also, we need to correct this one again here. So this is 11.19, okay? And let's calculate this together. So if we calculate now, 541.67 times 207 times cosine 7.77 minus negative, so this is plus 11.19. So the total power here will be 106,042.38 watts. So this is the amount of active power. And also, guys, by the same way, we need to calculate the reactive power. So we will repeat, and the difference is going to be only replacing the cosine by sine. So as you can see here, V times I times sine theta V minus theta I. So this is the same here. So the value will be 36,430.53 volts ampere reactive. And since the power factor is lagging, the power factor of the supply is lagging. So this means, guys, the reactive power is flowing from the source to the load. So this means the reactive power, the total reactive power here is inductive reactive power. So we can here write this is inductive because, again, because the power factor is lagging. So this is inductive reactive power. Part 4, we need to calculate the supply power factor. For sure, guys, we have all angles now, so we can say cosine theta V S minus theta I total equals our power factor, and you can substitute that here. So please correct this part also here. So this is 11.19. Okay, and let's calculate this power factor now. So the power factor is 0.9457. So this is correct. So it seems I just wrote the number incorrectly here, but I calculate everything from the calculator. So this is correct now. So this is the power factor and it's lagging again. Take care, guys. When you answer the power factor, you have to mention the magnitude of the power factor and the type of the power factor. If you answered only one of them, so this means you answered only half of the question. So you have to mention the magnitude of power factor and the angle of your power factor. Sorry, the type of your power factor. Last thing here, guys, find the power loss across the transmission line. Sometimes, guys, I see you make a mistake here, which is, if I say power loss, this means it has to be active power, because reactive power is not making losses. So all the time, loss is referring to active power. So this means I'd like to get the losses across the transmission line, which is across the resistance value, which is 0.2 ohms. So simply I can say now I squared times R, which is 207 squared times 0.2 ohms, which is 8,574.8 watts. So this is a power loss across the transmission line. So again, guys, the concept here in this problem, firstly, we need to calculate the main current. So in order to calculate the main current, we got the currents of the two loads. Then we added them together in order to get IT. Take care, guys, when you calculate the currents, you have to get I1 and I2 in magnitude and angle, because it's impossible to calculate the summation of current from RMS only. This is not DC. It's AC. You have to consider the vector angle. Okay, so we got the total current. Then we used Kirchhoff voltage loop here. We said Vs equals V load plus I times Z transmission line. We got Vs. So since you have Vs, you have current, you can calculate anything in this circuit. Okay, so this is a very important question. If I would like to say to you guys, I would like to get, let me add one more part here. So find reactive power on the transmission line. If I would like to get of the transmission, if I would like to get the reactive power of the transmission line, so reactive power means power across the inductor. So this is not active, this is not P, this is Q. So we can do the same like what we made here. So we can say now Q transmission equals I square times X L or X transmission. So this is going to be now, guys, the same current again, 207 to power 2 times the value of reactance of our transmission, which is 0.4 times 0.4. So this is going to be the reactive power across this load. Let me calculate this one. So 207 square times 0.4, it's 17,139.6. And the unit is volt ampere reactive. I can add one more question. I'd like to calculate the complex power. So part 7, calculate the complex power of the source. So complex power means volt ampere. So this can be calculated by many ways. So we can say here S equals the voltage magnitude times I conjugate. So this is going to be V. So V equals, we have the voltage magnitude here. So this is Vs. And take a copy of this volt. So this is Vs. Times the current, but the current conjugate. So this is our current. So multiplied by this current, but conjugate. So we have to reverse this angle from negative to positive. And this would be the value of complex power. Let me calculate this with you. So 541 at angle 7.77 times 207 at angle 11.19. So in polar form, this would be 111,987, and the angle is 18.96. So this is measured in volt ampere. Hey guys, so this is a way. We can calculate it in many different ways, but I don't like to make it like harder for you. For sure, you have the power, you have the active power, you have the power factor. So you can calculate S as P total divide power factor. So this is another way I can say here, S also equals P total divide power factor of the supply, but this is gonna bring the magnitude only, okay, not magnitude and angle. Okay, guys, so this is the absolute value of S. Okay, so this is an example, guys, of the power analysis for a single phase circuit. Now, let's move to another question here. So in this question, guys, in a balanced three-phase Y-Y system, so Y-Y means our supply is Y and our load is Y as well. The source is an ABC sequence set of voltage. So the voltages are ABC. And the load voltage on a phase is VAN. So the load volt on a phase VAN equals, okay guys, so please let's correct this here. This is not the load, I'm gonna say the supply. So the supply volt is VAN, okay? So this is supply volt, VAN equals 108 at angle 97.81. So this is the supply volt we have. And we have a transmission line equals 1 plus G, 1.4, and we have a load of 10 plus G, 13 ohms. We need to calculate the following. Firstly, we need to get the three line currents. So this is our power system. We have load, we have transmission line. So this is our load. This part is our load. This is the transmission line, and here is our source. Now we need to get the three line currents. Three line currents means I'd like to calculate IA, IC, and IB. Simply, guys, we mentioned before in such problems, we can convert this circuit to a single line diagram. So I said here, convert to a single line diagram and calculate the total impedance. So I can say, let me draw the single line diagram here with you now. So our supply is gonna be VAN. Then we have the transmission line impedance. Then we have our load impedance, and this is gonna be the neutral point, which will be connected to the supply again. So this is Z load, and this is Z line, and this is VAN. So now we can calculate the current easily. I can say this is IA. So we can say now VAN divide summation of these impedances equals IA. So firstly, I calculated the total impedance, and then I said VAN divided the total equals this current. So this is the given supply volt of VAN, and this is the total impedance we calculated. So we got a current of 6 plus or at angle 27.18. We need to check here something. We got the angle in positive sign. Does it mean the power factor is lag or lead? Again, don't be confused about the sign, because the voltage angle here is not zero. In order to be sure if the power factor is lag or lead, you have to draw the phasor diagram. So let's draw the phasor diagram, guys. I have here assume this is my reference, angle 0. I have the current 6 at angle 27. So this is current at angle 27 degrees, 27.18. So this is I. This is IA. And VAN is 108 at angle 79, which means this is going to be VAN. So again, from this figure, guys, is the current lagging or leading V? For sure, it's lagging V. So although the angle here is positive, okay, we said the power factor is lagging. So it's lagging V because the angle of V is higher than the angle of I. The V angle is around 80 degrees and this is 27. So this means I is lagging V. We need to get IB and IC. We don't need to make any more calculations. Just shift the angle by minus 120 degrees for phase B and plus 120 degrees for phase C. So this is the first part, which is find the line currents. Another question here, find the losses, and I declared here this is active power. So any loss, guys, means active power across resistance. Okay, so find the losses across the line impedance, and the line impedance is this impedance. So this doesn't mean we should say I squared times impedance, because by the end the losses is nothing but active power. So we should say I squared times only the real part of the transmission line. So again, this is the impedance of transmission line. So this is the Z transmission. So this is Z transmission, but this is the resistance of transmission, which is going to consume losses or consume power from this system. So if I would like to calculate the power, I should multiply I squared times R, not times Z. Just a moment, guys. We have here three-phase system. So this means we will multiply I squared R times 3. So the correct answer for part 2 now, we can say power equals I squared times R line. So I equals 6, R equals 1, but we have to multiply times 3. So this is 3 times I squared times R line. So this should multiply here by 3. So 3 times 36 is 108. So this is the value here should be 108 watts. Okay, so this is the power we could obtain, or sorry, we have power losses on the transmission line. Okay, let's see the second or the third part. Find the source power factor. So we know the value of VAN, magnitude and angle. We know the current as well. So we can say the power factor is cosine theta VAN minus theta IA. So this is simply power factor equals cosine theta V minus theta I. And the V is VAN. So this is theta VAN, and this is theta IA. So if you subtract these angles and with the cosine angle, it would be 0.6. And I mentioned here it's lagging. You have to mention again what the type of the power factor. And we understood it's lagging because we draw already the phasor diagram here, and it's very clear that the power factor is lagging. Let's solve the fourth part here. Find the overall active power absorbed from the source. So we need to get the active power absorbed from our voltage source. So this is going to be the total power. So we can say V times I times cosine theta V minus theta I, but we have to multiply this times 3. So this is 3 VAN phase times IA phase times cosine theta VAN minus theta IA. So this is the value of our active power. Another question here, guys. Find the overall reactive power absorbed from or returned to, because in the question in the beginning, we don't know, is it going to be lagging or leading power factor? So it could be either. It could be the power or the reactive power moving from supply to load if it is lagging, or return to the supply if it is leading. So here, for sure, since the power factor is lagging, so it's going to be only absorbed from the source or moving from source to load. So we can say now the overall reactive power absorbed from the source will be 3 times V times I times sine angle. Okay, so this is the way, guys, substituting the relation again and get the value of reactive power. And again, this reactive power is inductive. Why? Because it's lagging power factor. Okay, guys. So please, guys, I urge you to solve these two questions. Okay, calculate everything with numbers. And if you have any questions, send me an email. Please also review the homework you had before. Okay, and the midterm exam is going to be similar to the questions we have in homeworks or in this revision. Thank you so much, and see you. Have a nice day, guys.